So my second part of my lecture will be completely algebraic. So I think the large portion of my first lecture was kind of sketching differential geometry, the original idea from differential geometry, but the second part will be completely algebraic. So we will concentrate on modular theory. Actually, this is why I was becoming interested into K-stability like about 10 years ago. So slightly more than 10 years ago. So, but first, let's talk about some general modular theory. So I mean, if you are a geometer, you of course know that the modular theory is something like one of the most important powers, important tools in algebraic geometry. So if you are not an algebraic geometer, so roughly we just construct a space such that the point on the space precisely correspond to the class of objects which you are interested. So in our case, the class of objects are varieties. So you can think about it as a map that I give you one variety. I find the point on this map such that there is this one correspondence. And in general, there's hopeless to do this for all varieties. You have to post some assumptions this to make this modular space has some like reasonable properties. So I think this is a quite important feature for algebraic geometry, because if you study other type of mathematics, often when you want to classify them, if you move this, if you want to study how they move continuously, in some cases, for instance, in topology, if you move continuously, they're just the same object. So there's nothing interesting happen. And also in Riemannian geometry, for instance, you have to, if you move this, your Riemannian metric, it often move in an infinite dimensional space. So somehow you have to put a restriction on this, on how you vary it to make it to be reasonably nice. And for algebraic geometry, as long as your like a class of objects is reasonable, the modular space is often one algebraic object. But the thing is, you want to find this reasonable class. So that being said, let's look at the history about finding modular space for varieties. So the simplest case is the case when you study the modular space of curve. That's already actually very, very interesting. So historically, there was this analytic approach of studying modular space of curve by looking at something like Teichmüller space. This kind of like a analytic construction. But to us, the really most important, the important construction was done by Mumford using geometry invariant theory around the 50s and 60s. So he constructed a space which parameterize, which the points precisely correspond to curve, with a smooth curve with genus at least 2. So, and actually, for different genus of course, they form a different component. But if you fix the genus, then you have some like a coarser projectives variety. And later, Dudley Mumford indeed constructed a compactification of this MG called MG bar. And Dudley Mumford's compactification was through some like after theory. But then later, Gieseker showed that GIT also give a compactification, the construction of MG bar. Then people have asked the same question for higher dimensional varieties for many, many years. And the people concentrate on generalize this picture to high dimensional in the case that the C1 is negative. So I will say why, later I will explain why this case, people are interested in this case first. And when dimension equal 2, then Gieseker also proved that all the smooth one, you can use GIT to construct it. And however, it was much later people realized that GIT indeed cannot give you a compactification. It's not like the curve case. If you want to get a compactification, GIT is not the right theory. This was done by, I mean, this was expected by people at least by the people from some perspective for quite a while, but it was confirmed by Xiaowei Wang and myself. So GIT doesn't work in higher dimension. But then there was another alternative approach initiated by Collat, Schiffer, Baron in '88 to basically, instead of using GIT, they look at the Stelling-Manfors way to compactify it. Then they realized that the main recipe in this construction, the Stelling-Manfors to generalize to higher dimension, is something called the minimal program. And in the surface case, you have to study a minimal program of a surface of a curve. So it's a three-dimensional minimal program, which was actually a very hot topic in 80s. So that time, Collat, Schiffer, Baron realized that MMP can be used to construct the limit, construct the compactification. So roughly speaking, how do you get to the limit? Basically, you just start a family. You resolve in some like a reasonable way, and then you run MMP. And then, as long as you can run MMP, it's not very hard to prove. The output will be the same. So in other words, once you realize the MMP works, and you are given all the MMP results, then to say that the MMP gives you the limit to say this is not hard. And if you want to characterize what happens at the limit, it's some variety with similar canonical singularity with omega positive. So if you don't know similar canonical what is, it's fine. It's not needed in the rest of our lecture. And the main recipe of this, first, it needs a minimal program like people did in BCHM. And it actually needs some like a stronger result, like also the boundedness and some other minimal program result, which Hickman and I we wrote it in a bunch of papers, but the last one was in 2018. And also it needs local stability theory developed by Collat, 09 and 19. So and some other stuff as well. So it was people worked on this, from Coil's time 88 to 19. That was like 30 years. So people work on this for like some 30 years and prove all the needed property. So as the output, the theorem says that there is a projective scheme which parameterizes KSB stable varieties. And the KSB stable varieties are just varieties has similar kind of singularities with positive canonical class, which is similar as saying negative C1. But now we are interested in the opposite case, which is the case of Fano. So historically, I think if 10 years ago, when you ask most of our geometers, they would say there was no modular theory for Fano variety, and there was no hope to give a modular theory for Fano varieties, because historically, there were just too many pathologies for a family of Fano varieties. So, for instance, if you have a Fano manifold over puncture family, there are often too many possible limits, no matter what kind of condition you put. So, for instance, you can put a Fano condition, that's not enough. You can even put a smooth Fano condition, that's still not enough. And the smooth Fano is the best you can expect just through the minimal program theory. So basically, that just say the minimal program itself is not enough. I mean, in 2012, Chile and I proved that there is always some other kind of like a good limit in the inside the minimum program series. So more precisely, you can always get just using the minimum program itself, nothing else. You can always get a KOT final variety limit. But the problem is often too many. It's not unique. So this is not the right way, the MMP itself. So what's the solution? The solution, I mean, the slogan is, so all final varieties are equal, but some are more equal than others. So I don't know where you know this sentence came from. I mean, you can search online. So anyway, I mean, when you search online, you should replace final varieties by animals. So the original say all animals are equal, but some are more equal than others. Yeah. So anyway, instead of trying off n-dimensional final varieties, we actually look at the one with color metric, or algebraically, we just look at the stable one, right? Now we have this equivalence between some algebraic notion, so we can just use this algebraic notion to establish the modular theory. So historically, actually, this belief, I mean, you can have, people start to have some hope of this kind of belief, I think more than 10 years ago, because from the differential geometry work, that it was somewhat clear that the space of Callister metric is a finite-dimensional modular space. As I said, that when you have something like a finite-dimensional moduli, you often expect that this is some kind of algebraic object. And also, from the examples people wrote out, even before the modular theory was general modular theory was worked out, there were some examples people work out, and those examples also indicate that there should be, I mean, the K stability could give you a notion to construct modular space. But on the other hand, if you just use the definition of K stability itself to prove, because it's very hard, at least for quite a while, it was very difficult to understand how the stability notion vary when you have a family of final varieties. So for instance, you would expect that the stability should be an open condition, and also you should expect that you can always find after replace the special fiber, you can find a stable one, or also maybe the stability should be, the stable one should be unique. So all this kind of things which one need to establish the final modular final variety, it's very hard to, at least it was very hard to directly work with it using the definition of K stability. So, but anyway, there was like a huge progress in the last, I would say, 5 years or slightly more. And as the output, we actually have this K modular space. But the modular space is, even in the abstract level, it's harder than KSP, because the KSP theory, that was a Delimonfort stack with the coarse modular space. So even in the Delimonfort case, that it was like that. You have a Delimonfort stack. I think that was actually how Delimonfort stack was named after this Delimonfort's paper constructed the modular space of MG bar. And then you have a coarse modular space. But in the final case, because we have final variety with infinite automomial, this is not going to be true. What you expect, you can expect is some Artin stack, and this Artin stack is a stack which parameterizes all the K semi-stable object, and it's actually a global constant stack. But so for Artin stack, you cannot ask. So instead of asking coarse modular space, you can ask something called good modular space. And this actually admits a good modular space. So on this good modular space, the points precisely correspond to K polystable final variety. So in other words, if I work over C, the point here precisely correspond to the Einstein final variety. And this guy is not, so here I want to say admit the separated good moduli space. I want to say separated here, but it's actually not just only separated, it's actually proper. But the second step, we first prove it's separated, and then we prove it's proper, and actually it's projective, but we show some line bundle on that project. So again, the output is a projective scheme. And the proof of this theorem is purely algebraic, as I said. And if you look at the original CDS10 work, it gave you a lot of recipe to construct the modular space, but only for the one component, which is the component that the generic point is smooth guy, and you construct the compactification. So the original analytic approach was quite powerful to construct a moduli for this component. But if you want to construct the moduli for the entire one, so far there's only algebraic approach to do it. So here is a picture of some people contributed to this construction of K moduli. I mean, I think some of them may be even in this talk. So this is, I mean, from the left to right, that was Ziquan Zhuang, myself, Yusen Liu, Charlie Stevens, Xiaowei Wang, and Howard Blue. So first, let me talk a little bit about the uniqueness. So what does uniqueness say? Uniqueness say that, if I have a two family of Fano variety, and over a pointed curve, and if we assume outside one fiber they are isomorphic, then the uniqueness should say that the special fiber are also isomorphic. Of course, as I said, for general Fano varieties, this is not true. So you have to pose some stability condition. Then the stability condition you can pose is that the two special fiber, they are K semi-stable. And again, if your moduli is a separated Delimonfort stack, then you ask yourself whether you can extend this isomorphic across this point, such that particularly the x0 and x0 prime is also isomorphic. Again, as I said, this is not true actually, because we are not dealing with Delimonfort stack. We are dealing with Arden stack. So the x0 and x0 prime are not isomorphic right on the nose. So, but we show they are S equivalent. So if you are familiar with the moduli of vector bundles, so you know for vector bundles, this is also the case that if I have a family of semi-stable vector bundle, I might have two different semi-stable fill-in, but they have the same S equivalence class. So in other words, if you take the Harder-Narasimhan filtration of these two, if you took the Jordan-Howder filtration of the two K semi-stable bundle, and you take the direct sum of them, then they become isomorphic. So that's what the S equivalent means. In the final case, the S equivalence is something like this, but much more complicated. But we can describe it abstractly. That's easy. So basically, we just say x0 and x0 prime, they have a common GM equivalent K polystable degeneration. So the x0, x0 prime, they might be different, but they degenerate to the same K polystable Fano varieties through the GM degeneration. So that's what S equivalent means. So the uniqueness holds in this sense. And one can actually upgrade this work by Bloom and myself to, and once actually to use some like more general theory. And once you upgrade it, you got some like a very nice application. For instance, you prove that the K polystable Fano variety, the automorphism group is reductive. Again, as I said, if you assume current symmetric on the smooth one, this was Matsushima's work. And if you assume a singular Kainstein metric, that was actually much harder to prove. This was in CDS10. But now there is a completely algebraic proof of this. So actually, what in this paper, in this Harper Bloom, Harper Leisler, my paper, which enhanced this paper by Bloom myself, was showing that this moduli has a separated good moduli space. So you might not have heard what good moduli space is, but now we are in 2020 to actually 2022. So I think that in 2010, people were still mostly working on the Riemann stack and the coarse moduli space. But somehow, kind of miraculously, in the last 10 years, there are a lot of modular problems in algebraic geometry, which is not the Riemann stack anymore. It's a Ardeen stack. And then people still want to say whether this Ardeen stack has something which behaves like a coarse moduli space for the Riemann stack. And this was actually, this theory, there was one person who spent his actually essentially a whole career to develop this theory. That was General Upper. So he developed something called good moduli space. So locally, the good moduli space is just behaves like a reductive group acting on some affine space. So if you have a reductive group acting on a affine space, the stack is just the stack quotient. But the good moduli space will be just the GIT quotient, which is just the spec of the invariant function ring. So in other words, the good moduli space at locally is just the stack from the quotient by reductive quotient on a affine variety to the invariant function ring. So there is nothing fancy about it, but this thing has many good properties, and this is just at locally. So to get a good moduli space, there is also some like a global condition to how you can glue this everything at locally. But in our case, we actually get a separated good moduli space. So one key recipe was some like a general theory on when good moduli space exists by Harper Leisler, and Henlos. So this theory basically is the analog of Kilmore theorem to the Riemann stack for Ardeen stack. So of course, I mean, people applied Kilmore theorem for many years to studying the Riemann stack. As I said, now many questions are Ardeen stack, and this is the corresponding result. So once you have this uniqueness, we want to prove the moduli, the good quotient moduli space is proper. So that just boils down to, if I have a family of Fano variety, such as the general fibers are K semi-stable, I can always fill in the limit to make it to be K semi-stable. So a while ago, Chili and I proved that you can always fill in the limit to be a Fano variety, KLT Fano variety. But the issue is where this K semi-stability come from? How do I construct a K semi-stable instead of just a KLT Fano, but a K semi-stable KLT Fano? And the answer is we don't know. Actually, even now we don't know how to directly construct it. We only have an indirect way. So the indirect way is somewhat so-called like a Lanton method. So Lanton method is basically use the Lanton method to prove the properties of the stack. The moduli space of vector bundle without using GIT. So what Lanton did is he just have a family of vector semi-stable vector bundle. He constructed any limit which is vector bundle. If it's stable or semi-stable, then he is done. If it's not, he basically have some operation to increase the stability of this bundle. And then he showed there are only 5 many steps. So after that, you end up with a semi-stable bundle. So each time, if you are not semi-stable, you increase your stability a little bit, and then after 5 many steps, you will terminate with a semi-stable bundle. So here we do the same thing. That was Bloom, Harper-Leisler, Liu, and myself prove. Here we prove that assuming the optimal degeneration theorem, which I wrote here, we assuming this is true, then we can, so for any final variety, we can define some invariant. Roughly speaking, that's the delta invariant. So which I defined at the beginning. So remember, delta larger or equal to 1 is equivalent to say this is K semi-stable. So if you have a limit, delta is less than 1, then you just operate it. You find another limit, then you show delta increase. And then you show delta can only increase 5 many steps, and then delta will become 1. So somehow we don't have a direct way to construct a semi-stable guy. We really just have to use this abstract approach to say that there's this way of increasing the stability to find the replacement is not direct. It's not direct. We just show there is one. So if someone can figure out how to construct this semi-stable limit directly, I think that would be very interesting. That would be very interesting. I mean, for instance, in this like CDS10, in the smooth case, they do have a process, right? They have a process. I mean, different geometry, they just construct this Gromov-Hausdorff limit. And algebraic geometry, slightly more algebraically, they use an orthonormal basis embedding their variety into Pn, and then they just take the Chow limit. That will be the stable guy. I mean, here we really don't have a direct way to construct any direct algorithm to construct the limit. But anyway, to prove the properties, we just show we have one, and although it's not direct. So, but in this paper, this like a BHLX paper, we module one theorem, we module one conjecture. That time was conjecture, now was a theorem. Is that we module that when delta x is less or equal to 1, there always exists a divider, calculate delta. So again, this was in the end of my first part, I say that a key part is to prove uniform stability is equal to K stability, for which you have to show the delta is always reached by some divider. It's not just an infimum, but it's really reached by some function. For there, we only need the case delta equal to 1. But for this modular, we actually need the delta also less than 1 case. So we basically we need all the case for delta is less or equal to 1. So again, I mean, there are 2 steps as I explained. The first step is we show there is a quotient monomial valuation such as this is true. So in some sense, quotient monomial valuation is like the divisorial valuation, but the divisorial is kind of the rational version. The quotient monomial valuation is like the real version. So, but to prove this, we need the Berkas proof of the boundaries of complement. And to get from the quotient monomial valuation to divisorial valuation, we have to prove some finite generation statement. So this is not the finite generation statement appear in BCHN because we are looking at the gradient ring for some valuation, but this valuation is not divisorial. If this is divisorial, then this finite generation can follow from BCHM without too much work. But here we really have to prove for some quotient monomial, so we have to really develop a new method. But once you prove this, you can easily prove that this quantum valuation, if you perturbate it a little bit into some dividend valuation, then this number will be the same. So you find the dividend valuation calculated. So here the ring is basically just the coordinate ring of the final variety. And then for final variety, of course, I mean, if you have a valuation, you just take the valuation on the section. So for each fixed H0 minus MKX, this vanishing order along this valuation give you a filtration. And then you can look at the gradient ring of this filtration. And then you put in all the jumping number together and all M together, that form a ring. And my question is whether this means the fine generative. So this is basically just the copy of the theorem at the end of the last page. As I said, if it's dividend from BCHM, but for higher rank, we need a new thing. And the key is, the theorem saying for V, which calculates the delta X, but what we really need is some like birational geometry condition to guarantee the fine generation. So we have to sort out what is a birational geometry condition. And the original way for dividend case is the valuation. I mean, here, so it's a little bit technical. The valuation is the LC place for some complement, but actually that's not enough. So being a LC place of a complement is enough for dividend valuation to have a final generated associated gradient ring, but it's not enough for higher rank valuation. So you have to post like a strong condition. And we actually spent quite a while to sort out the right condition. The right condition say that this is the L place of some special complement. So what's special complement? The special complement just say, if I fix a log resolution, my complement, if you take the birational transform on this log resolution, it contains an ample divider, which this ample divider doesn't contain any strata. So in other words, this complement give you some small ample divider to wiggle, to perturbate, to do this kind of a tie break argument. So that was, this seems to be a technical assumption, but actually it's very important. It's a key observation to say that this condition imply the valuation always have an associated gradient ring. And the original proof I found with Yucheng and Zichuan, we use abundance of final variety. But later this year, we found a proof which we can circumvent the use of the abundance of final variety. So particularly this same theorem can be used into local case. So the MMP input of the theorem is really just the BCHM. We don't need the abundance of final variety anywhere. So I mean, if you are interested in the proof, we can talk about more, but the self is a little bit technical. But somehow this higher rank evaluation, this fine generation for higher rank evaluation is really completely new problem for birational geometers, because I think this might be the first time some natural valuation, the fine generation of some natural valuation really becomes so important in the geometry question. So then I want to talk a little bit about the examples about what the final moduli look like. So for the dipolar surface, Mabuchi-Mukai first showed that, degree 4 dipolar surface is not just the intersection of two quadrics in P4. And then Mabuchi-Mukai showed that GIT moduli is the same as the K moduli. And for degree 1, 2, 3, the smooth part, I mean, by 10th theorem, we know they all have a chiasymmetric. And then Odaka Sporty-Sun also found what's the commodification of the smooth locus. So for final varieties, and And this is for the smoothball component, everything is no. Then there are some interesting examples where K moduli is equal to GIT moduli. So for instance, I said the degree 4 Dipole surface, but actually that's true for degree 2 of quadratic hypersurface in any dimension. So that was proved by Spotty Sun. And also for cubic threefolds, this was proved by Liu and myself, and also fourfold by Liu. Actually, we expected this for all cubic hypersurface. That's the GIT moduli of K cubic hypersurface is the same as K moduli. But now, for now, we can only prove it up to dimension 4. Then there are also some other new perspective, I think, introduced by Kenny Asher, De Fleming, and Yuchen Liu. So this study is something like a wall crossing. So I mean, if you study geometry moduli spaces, often there are some like a wall crossing. If you change your stability condition or change your this stability condition is a vague term. For instance, it could be change your linearization of your lie bundle, or it can change the Bridgeland stability. So here, one just change the. So one example is we fix the P2, and we look at the divider. So then we can talk about. Then we look at the range when it's a log funnel. And we study the K stability by putting different coefficients on that. And then they prove that when you put a different coefficients, it's also wall crossing. So there are basically 5 Manning wall. And there are some like a wall, when you cross it, it looks like a local GIT. So this one was proved. And they also work out all the walls for the case like a P2 conic curve. Also P1 plus P1. And the 4-4 curve, and also P2, P3 cortical surface, and many other examples. I think they are probably working now. And another very active subject is looking at the classification of smooth funnel threefolds. By the result of Iskowski, Mori-Mukai, we know there are 105 families of smooth funnel threefolds. I think Chersoff and his group built on previous works by others show that there are 70 plus family contains the general members are K semi-stable. And then you can naturally ask whether all the smooth members are K semi-stable. And most of them are. I think there are, actually, we probably conjecture all of them are K semi-stable. And most of them are even polystable with some exceptional case, like the famous deformation of Mukai-Murray proved by Tian. And there are some other examples in other cases. And also you can even ask much harder questions, what are the corresponding K moduli space? So it's just not a smooth, but you can also ask what are the corresponding like a singular K limit. I think this is a much harder question because somehow to prove the singular funnel variety, it's harder. And there are some examples people already work out, like here the cubical one, also the intersection of 2 quadratic hypersurface in P5, and also there are some like a one-dimensional. There are some example when the moduli space is one-dimensional, and then I think Chersoff and his group find some other one. So I think this is an active subject. I think many people are working on it. So basically, I think that the theory of funnel K moduli now give people a completely new playground to study moduli space, and hopefully it can connect to some other problem as well. Okay, let me stop here. Thank you very much.